All right, we pick up in section 4 the pH scale. The pH is the negative logarithm of the hydronium ion concentration. Pretty straightforward. We'll do a little review here. As the hydronium ion concentration increases, the pH is, of course, going to go down. So this negative log thing is called the P function. And therefore, the concentration of hydroxide ions will be called the pOH. And pKw would be the negative log of Kw, which since we know is 1 times 10 to the minus 14th, that makes our pKw equal to 14. So that's very, very convenient because now we know that pH plus pOH is equal to 14. This is going to be very advantageous to us when we do some calculations. So now we're going to fill in this table. At this point, you should have your calculator in your hand, and you should be able to convert back and forth between pH, pOH, H plus, and OH minus. So we're given H plus. We can take the pH of that because it's the negative logarithm of it. We can get the pOH by taking 14 minus 4.6. We can get the OH minus 2 ways. The first way is to divide Kw by H plus, since that's part of the equilibrium expression, and we get this number. Or we could take 10 raised to the negative pOH, because algebraically that is what the OH minus concentration refers to. So when we do all these three problems, you're given one of these, and you have to calculate the others. And of course, it's acidic if the pH is less than 7. It's basic if the pH is greater than 7. In the laboratory, we can do this with a meter. Pretty straightforward. We could also elect to use these organic acids, which are very color sensitive at particular pHs. So in this question, we're asked to to use this figure to estimate the approximate pH of each solution. For solution 1, we want methyl orange to be orange, methyl red to be red. If I look carefully at this chart, methyl orange to be orange and methyl red to be red, that's got to put us somewhere in this pinkish block here. So our approximate pH is about 4. With these indicators, we cannot get an exact pH, just not possible. But we can get an eyeball approximation to typically within half a pH unit, sometimes even less. All right, now your job is to look at each one of these solutions and for these color ranges, determine what the approximate pH is. That will help us decide, okay, what indicator do I want to use for my particular problem? And when you do that, I got the following pHs. All right, section 5. We're going to talk about strong acids and bases, and we want to explain why double arrows for equilibrium are not used in this reaction. Well, that's because nitric acid is one of our strong acids. It's completely dissociated, and there just isn't an equilibrium. So I'm going to write how chloric acid, which again is one of our strong acids, how does that behave in water? It just dissociates. The H on the HClO3 is donated to the water, giving us the chlorate ion and the hydronium ion. Now, with strong acids, the concentration of H plus in the solution is the same as the concentration of the acid itself. So for this particular case, we want to take the negative logarithm of 0.50. Remember that the rules of sig figs are slightly different for acids and bases in pH problems. If the concentration of H3O plus or OH minus has 2 sig figs, the pH has 2 decimal places. The number to the left of the decimal is not part of the significant figure determination. So at 0.5, we can do this and we get a pH of 0.3. Negative log of 0.0075 is 2.12, so on and so forth. Now, this last row in this table was very dilute. And did you notice anything strange about the pH value? Let's flip back. This concentration said that our pH was 7.82. But that's a problem. The reason it's a problem is because if it's acidic, the pH is simply not going to be greater than 7. So the pH of a very dilute acidic solution will never rise above 7 just because it's very dilute. It will approach the concentration of water, and therefore the pH will be equal to 7. Now we want to calculate the concentration of nitric acid for each of the following solutions. This is a reverse. We take 10 raised to the negative pH. When we take 10 raised to the negative pH, you should do this on your calculator. You should get these 4 concentrations for our concentration of HNO3. And the reason it's the concentration of HNO3 is because there is 1 mole of HNO3 for every 1 mole of hydronium ion. Now, let's look at bases. Strong bases are the hydroxide compounds of alkali metals such as sodium and potassium, or the heavier group 2 hydroxides. And we want to fill in the information that's missing in this table. It's just very much like the last set. All right? So if I have 0.25 molar NaOH, that must mean my pH is 0.25. Sorry, my OH minus is 0.25. So my POH is 0.6. My pH is 14 minus 0.6, or 13.4. And I can do the same thing for a more dilute solution of potassium hydroxide. And I can do the same thing for calcium hydroxide. But there's something extra that happens here. When I go backwards in this problem, I've got a pH of 10.23, so POH will be 3.77. And for sodium hydroxide, my concentration of NaOH is 10 raised to the negative POH. And so these numbers are pretty straightforward. But when I look at strontium hydroxide, I see that I have 2 moles of hydroxide for every 1 mole of SrOH2. And so easy enough to get the POH, but now the concentration of SrOH2 is 10 raised to the negative POH, but then divided by 2 because of stoichiometry. All right, section 6, we need to talk about a weak acid. One of these 2 diagrams works for a weak acid and one doesn't, and the one on the left is the one that works because it partially dissociates, whereas the one on the right would be a strong acid. Now, if we write a weak acid as just HA, hydrogen plus some acid anion, I'm going to get this dissociation, and because it's a weak acid, there's an equilibrium set up, which answers part C. Now we want to write our K expression. It's very similar to all the things we learned in the equilibrium section. K will be H plus times A minus divided by HA. Now, which of these 2 substances is stronger? We've got to justify our answer on the why we make the selection we do. The larger the Ka, the stronger the acid. The larger negative exponent in Ka means the equilibrium constant is very small, which means it's going to be a weaker acid. Now, many organic acids contain a carboxylic acid group, CO2H. Sometimes you see this as COOH. We want to circle the acidic hydrogen atom. That would be the hydrogen attached to the oxygen in the COOH portion of the molecule. So we've circled these 3 right here. Now, if you're given the concentration of a weak acid in the pH, you can calculate Ka. So here we have the structure of nicotinic acid, which is also vitamin B3. And we want to write an equation for the dissociation. Again, we just write our formula out. We lose the hydrogen because it's an acid to form H plus the anion. And now we can write our acid dissociation. Again, notice no water molecules. Liquid water will not be part of the equilibrium expression. A 0.020 molar solution of nicotinic acid has a pH of 3.26. Now we want to calculate the concentration of H plus in this acid. Well, we know that pH is the negative log of H3O plus, so I can take 10 raised to the negative 3.26, and I get 5.5 times 10 to the minus fourth. All right, now we want to use a Rice table to determine the concentrations of the original acid, H plus, and the anion in this 0.020 molar solution. So we set up a Rice table just like we did in the equilibrium section. We write our reaction. Our initial concentration is 0.02 molar acid, no hydronium, no nicotinic anion. My change is going to be 5.5 times 10 to the minus fourth. I'm going to gain 5.5 times 10 to the minus fourth hydronium ion concentration. We got that from our pH problem. And we know that we're going to gain the same amount of the anion because stoichiometry tells us we will, and therefore I'm going to lose that same amount of the original nicotinic acid. All right, so at equilibrium, I can subtract 0.020 minus 5.5 times 10 to the minus fourth, and I get approximately 0.019. That's true if I look at sig figs. The other two are 5.5 times 10 to the minus fourth. Now I'm going to compute Ka. I just plug in my two numbers for the denominator and my two numbers for the numerator, my one number for the denominator, and now I have my K, 1.6 times 10 to the minus fifth. All right, we're going to define percent ionization. And this is going to be important for us as we try to determine how much algebra am I going to have to do when I solve these problems. We'll get to this in a little bit, but right now we're just going to define and do some computations for percent ionization. Now this is defined as the concentration of the ionized acid divided by the original concentration, and then times 100 to convert it. All right? So here we can see the percent ionization is the hydrogen ion concentration at equilibrium, which is 5.5 times 10 to the minus fourth, divided by my original concentration of 0.02, all times 100, and I get 2.8%. Now we can work this problem backwards. Hypochlorous acid has the formula HOCl, so when this thing dissociates in water, I get H plus and OCl minus, and of course I can write my Ka, my equilibrium for my acid concentration, and I get this. All right, now the Ka, we're given the Ka, it's 3 times 10 to the minus 8th, and I set up my Rice table. I know my original concentration is 0.020, and I have minus x, and plus x, giving me these values right here. Now, the interesting part here is I have this denominator that if I don't do something to simplify it, I'm going to have a quadratic. Now, we can solve quadratics, but we don't always have to. If we make the assumption that x is insignificant compared to 0.020, then the denominator just simply becomes 0.020. X is so small, we can ignore it. And if we ignore it, we can simplify this expression and get x is 2.4 times 10 to the minus fifth. pH is 4.62. And our assumption is going to be that if percent ionization is less than 5%, we can make the simplifying assumption and don't have to do a quadratic. And with that, we're going to stop again and go on to the rest of it in the next video.